As we move into Module 4, we're going to be discussing quite a bit about phases of matter and about how the intermolecular forces in between the atoms and the molecules that make up a substance are going to affect the phase of matter that a substance is in. Now, the phase of matter is going to depend on two things. The first thing is the relative strength of the van der Waals forces, or the intermolecular forces that are between the atoms or the molecules of a substance. Now, he just barely mentions it in this section, but we're going to spend practically the rest of the chapter talking about these types of forces. And they're not forces that you're not already unfamiliar with. For example, you're going to have an electrostatic attraction between ions of an ionic substance. For example, sodium chloride, you're going to have a positive sodium ion and a negative chloride ion, and the positive and negative charges are going to be attractive to each other. That's an example of that type of an intermolecular, or in that case, an interionic force. You are familiar with the concept of hydrogen bonding. We talked about that extensively, whether you were in physical science with me, whether you took chemistry with me, both of those we talked about hydrogen bonding, and that is an example of a van der Waals force as well. So anytime you have any type of force between the molecules of a substance that's going to tend to hold them together, that's going to affect what phase of matter that particular substance is in. The second thing that's going to affect the phase of matter is the energy of the constituent atoms or molecules. And the reason that that's important is because those molecules have to overcome those intermolecular forces to either be able to move apart from a solid to a liquid form and get further apart so that the molecules can actually slide past each other instead of just stay in one place and vibrate. Or if they're in the liquid phase already, they've got to be able to have enough energy to completely separate themselves from the rest of the substance and move into the gaseous state, okay? Now, that energy is going to be dependent on a couple of different things. Mostly it's dependent on the temperature, because as you've already reviewed in the first section, the kinetic theory of matter tells us that the faster substances, molecules are moving, the higher their temperature is, or the higher the temperature, the faster the molecules are either vibrating or moving around. So as you increase the temperature of a substance, you're also going to increase the energy of the substituent particles. However, it's also important what the atmospheric pressure is around that substance. Now, while it is important for a solid, it is even more important for a liquid, because as you increase the pressure, if you think about a liquid in a container, the atmospheric pressure is pushing down on the surface of that liquid. And so for the molecules to be able to escape, it's got to push against the atmospheric pressure that's pushing down on it. So the more that you increase the pressure, the atmospheric pressure, the more energy that you're going to require for these molecules to be able to evaporate into the gaseous phase. We will go into a whole lot more detail about that as we move into the chapter, but those are the basic ideas behind phase changes. I wanted to mention the evaporation process because it can be kind of a confusing concept almost, that when things are evaporating, they actually are cooling down, which doesn't seem right to us, because normally, especially if you think of water boiling on a stove, you're like, well, that's hot. How is that possibly cooling down? He does explain it in the book, just real briefly though. When you get to the point where you have a molecule at the surface of a liquid that's going to escape, that is one of the few molecules in the substance that actually has enough energy to be able to escape into the gaseous phase at that particular moment in time. Once that molecule escapes, it takes all of its energy with it. And since that molecule had more energy than most of the other molecules in the substance did, the whole container then is going to lose energy. When it loses energy, the temperature is going to go down. And so that's why we say that evaporation is actually a cooling process. Eventually, you're going to have more energy absorbed. If it's specifically an evaporation process, you're going to have more energy absorbed from the surrounding air so that eventually more of the molecules at the surface will gain enough energy to be able to evaporate. Now, if you're talking about a boiling process, then obviously the heat source underneath that is where the additional energy is going to come from. You'll also remember that sweating is a process that cools you off, and energy is needed for that, for the water to evaporate from your skin. Okay, so that may help you to remember the idea as well. There are a couple of graphs I want to mention just really briefly. The first one is a graph that he had, again, it was in the book, where we've got number of molecules on the y-axis and we've got the molecular energy on the x-axis, and we've got this curve here. And the thing I wanted to point out to you is the difference between the most probable energy and the average energy, because I think that concept can be a little bit confusing sometimes. Average energy means that if you take every single molecule within the substance and you average together their energies, you're including not only the ones that have a smaller amount of energy, but you're also including the ones at the surface that are just ready to evaporate and break away. Okay, assuming that we're talking about a liquid. We're talking about the average of all of those. However, you have very, very few molecules that actually have enough energy at any moment in time to evaporate. And that amount of energy is indicated by this part under the curve over here. These are the molecules that actually have enough energy at a particular moment in time to evaporate. And so they are included in this average, but the vast majority of those particles do not have that amount of energy. And this is going to kind of push that average up, this higher energy needed to evaporate. So that's going to push the average energy a little bit higher. But the most probable energy means that if you would say, if I have this particular amount of energy right here, how many of the particles in the entire container are going to have that amount of energy? You're going to have more particles that have a lower amount of energy than the ones that have the average amount, okay? So this is number of particles, so you've got more particles at this level than you do that have the average energy. There's not a lot of difference between the two of them, but there is a little bit, because this right here has got to factor in this energy required to evaporate, which is very, very high. Okay, so I wanted to explain the difference between those two. And the other graph is one that you should remember from your first year chemistry course. Whenever you have a phase change, and if you look at this graph over here, on the y-axis, I've got temperature, so this is going to be increasing temperature, and the x-axis is going to be as I add heat to a substance. This is a heating curve, and so from here to here is where I have a solid, and I should probably write that in. Here I'm going to have a solid, and I'm going to raise the temperature of that solid gradually. Eventually, the temperature rises enough so that that solid is going to start to melt. So right here is my melting point. You will notice that the curve at this point is flat, and hopefully you will recall that when a substance is in the middle of a phase change, the temperature of that substance will not change, because the heat that's being added has got to go into giving the molecules enough energy to separate themselves from the solid and get into the liquid phase. So during the process of melting, the temperature does not rise. Once I get to this point right here, I now have a liquid, and I can raise the temperature of the liquid until the point where the liquid starts to boil. And once again, where the liquid boils, the temperature is now going to stay constant until the time that all of the liquid has evaporated. And then once I have everything into the gaseous phase, the temperature will once again start to rise. So if you are boiling water on the stove, my husband used to laugh at me when we were first married because I would put water on the stove for pasta for dinner that night, and I'd have the burner cranked all the way to the top. And he would laugh at me and he'd say, "You don't think you can make the water boil at a higher temperature, do you, just by turning the heat up?" And I said, "No, I'm just trying to get it there faster." Once it starts boiling, I would tend to turn the heat down some because I wasn't in such a hurry anymore. I mean, I was hungry, I was ready to eat. So, I wanted to add the heat quickly so I could get to that boiling point more quickly. But once that water starts boiling, it's not going to go, assuming that you live at a standard atmospheric pressure. Once that water starts boiling, you can't get it up above 100 degrees because it's going to stay at 100 degrees Celsius until all of it has evaporated. Okay, so I wanted to make sure that you remember that very, very important point from your first year course.